So this is a review of the force acceleration content. As a reminder, there's 3 lessons. All 3 of them are covered in this video, even though we only went over them in 2 separate classes. So I just kind of merged all of the content. So just a quick intro, right? So because things are moving, we have to consider why they're moving, and then because that motion has to come from why it's moving, you can set it equal to the motion itself, right? So kind of looking at the basic component of force acceleration, it's that the free body diagram is going to end up equaling the kinematic diagram, right? So basically, that means that you have to draw both a free body diagram and a kinematic diagram for each body in the system, right? So for free body diagrams, that's the one that talks about why things are moving, right? And it only has the forces acting on it. It doesn't have anything about the motion itself. Some things you could include or should include: the weight, normal force, friction, and any other applied forces or couples on the body itself. And then a couple things to remember, especially between weight and normal force, is that weight always moves directly down, like 100% vertical in the downward direction. Normal force always acts perpendicular to the surface. So if the surface is horizontal completely, like if this top of this picture was the surface, the weight would be going straight down and the normal force would be going straight up, so they're in the same direction. But if it's at a slant, right, you're going to end up having a weight that goes straight down, but a normal force that kind of goes off in one direction. And that's important to remember because a lot of people were drawing weight always parallel to normal, but in the opposite direction. And that's not correct. It always goes directly down. So that's the free body diagram. You guys have been doing that for a while, so you should probably hopefully be familiar with that. Kinematic diagrams talk about how the body's moving. So you don't have anything about the forces anymore. So there shouldn't be any kind of like tensions. That was, for one reason, that was one of the ones that always seemed to show up on your guys' kinematic diagrams was the tension. But none of the forces goes on the kinematic diagram. They all go on the free body diagram. So when you're building your kinematic diagram, you sit around and ask yourself, how does the body, how is it allowed to move? So if the body is allowed to move in like the horizontal direction, you have mass times acceleration in that direction, right? In the horizontal. If the body moves up and down, you have mass times acceleration in the y direction, right? And if the body is rotating, you have ig alpha, where alpha is the acceleration and ig is the center of mass. And this is essentially, this is the equivalent formula for ig. So usually you'll be given k, you use that formula, and then plug in for alpha. And then to solve these problems, all you do is set those equal to each other, and basically what's going to happen is you'll have some forces acting in the x direction and then some motion. So then it's logical to conclude that the forces acting in the x direction equal the motion acting in the x direction. So there's that. A quick tip is, especially for the things that are on a slant, you're going to have a lot of forces going parallel to or perpendicular to that slant. Usually it's just the weight that's not. So a quick suggestion is, if you're comfortable doing it, you can use parallel and perpendicular axes. But when you go into solving these equations, you have to verify that any forces in the parallel direction would be equal to motion in the y direction on another body. So you just have to verify that. Oh, I kind of already went into this. But this is a pretty much breakdown of what goes into free body diagrams. Weight's always straight down, normal's always perpendicular to the surface. Usually you end up solving for normal force, especially because a lot of times it goes into friction. Friction, I wanted to talk about really quickly, the difference between mu sub k times n and like solving for friction. So friction's always parallel to the surface that the body's on, and it acts in the opposite direction that the body moves. That's been a thing for a minute. But there's two different cases that you'll use friction, right? So if it's something that's clearly sliding, there's no doubt in your mind that it only slides, right? Then you can substitute mu sub k times n, right? So if it's a box sliding down a slope, the friction force is going to equal mu sub k times n. But if it's a wheel, you can't automatically substitute that. So because a wheel could be slipping, so there's, remember, no slip wheels, there's also slip wheels. No slip wheels travel along the ground, and that's how like cars move, right? They spin and then you move along the ground translationally. But if you slam on your brakes, your tires will spin. If you step on the gas too hard, your tires will spin, stuff like that. So it doesn't necessarily have to move translationally just because the tire is spinning. So this only works if there is sliding going on. So what you have to do is you have to actually leave friction as an unknown and solve for it and compare it to this value. So in the case for a wheel, you leave F of friction unknown. And then applied force, again, it's in the direction that it's given. All of these are pretty straightforward. It's just mass times the acceleration in whatever direction you're looking at. You shouldn't have any kinds of forces on your kinematic diagrams, and it's important to know that it doesn't really matter what direction you think it's going to go, because if you get it wrong, it's just going to come out being negative. So you don't have to stress too much about that. So really quick tips for problem solving. These are the steps that our professors have defined for us. Pretty straightforward. You pretty much classify motion, list what properties you're given, and then draw the diagrams and solve them, right? The thing that I wanted to clarify is what you have to include, what's not optional to get the maximum number of points, right? So writing the like types of motion on the diagram is not optional. You have to do that. Actually physically listing out the properties, you have to do that. Drawing a complete free body diagram and kinematic diagram, you have to do that. A lot of people skip, especially these steps. A lot of people skip these steps. Some people even skip this step and just try to go right into the equation. It won't work. You'll probably get 20 points out of 100 for just these 3 steps. So there's that. And then obviously you have to fully write out the equations and then show all your work. There's 2 quick special cases. I kind of went into this one a little bit, maybe, assuming. Nope, never mind, I haven't. So if the box is being dragged, I went into this one. So if you know that it's being dragged, you can assume this. But if you don't know, if you're even a little bit unsure, you can't. So the benefit is that it replaces that unknown with an unknown you already have to solve for anyway, but you can't do that unless you're positive that a box is sliding. The second case is like a simplification for wheels. So if you assume no slip, right? Remember how I said you have to solve for friction and assume that it's not slipping, right? So if you assume that, you have to solve for the friction force and then check your assumption. But by assuming that, you simplify the setup of the problem, right? So remember what the simplification for a no-slip wheel was, is it's the point of contact between the ground is the fixed end of a raffle stick. Then the center of the wheel moves one way or the other, right? Based on the acceleration of that center point being alpha r. So basically what that means is in like your kinematic diagram or in your equations, you can simplify magx, like motion of the center of the wheel in one direction or the other. You can replace that a with alpha r, where r is the radius of the circle, and that eliminates ax as an unknown. So again, it's pretty simple. You just have to remember to do it because it really simplifies the problem. And then this is just a reminder to come to office hours. I know I've had like a pretty busy week the last week or so, so I've had to cancel a couple of them, but I should be back to normal now. So be there, be square. All right.